Alrighty, it's time for a little update on Aries. Aries is a research project that I've been working on for the past about 4 months and recently published a research paper about it on ResearchGate, which you can view for free at the link in the description below. The point of this research project is to lay down the foundation to be able to visually identify flying aerial objects, including drones, aircraft, and even asteroids or planets, using only cameras and only simplistic sensor data. However, these simplistic sensors are then distributed and then fused together again in a process called pixel-to-voxel projection, as dubbed by Consistently Inconsistent in his video. For my equipment, I'm using a $20 Orange Pi 03, an Arducam with a 180-degree lens, and a PLA printed housing body. And for my target drone, I'm using a Potsenic, I think it's pronounced, very standard small drone, nothing special about it, but it can be programmed to fly in a grid, which is what I'm going to be using it for. My plan is to head out to the same baseball diamond I've been using for earlier tests and place one camera on each base of the baseball diamond. Camera 1 on base 1, camera 2 on base 2, etc. The exact orientation of the cameras as I'm placing them on the base doesn't actually matter, and I'll explain why later. As per usual, I'm taking off from the pitcher's mound. And let's get her started. Here's the drone taking off, and each and every camera, camera 1, camera 2, and camera 3 can see the drone, so I know everything is working properly. Earlier I mentioned that we don't need to know the exact orientation of the cameras as we're putting them down because we're going to be using what's called point-in perspective. In short, I'm going to fly a drone to known GPS locations and then mark on the screen where those GPS locations appear to be in pixel space. Then using some very simplistic math using the GPS locations, their corresponding pixel locations, and the camera's distortion value as inputs, I can get the camera's rotation matrix as an output. This rotation matrix tells me the exact absolute orientation of the camera and a 3x3 matrix. Or in this case, I'm going to be using a very simple program that I wrote up in HTML and JavaScript in order to do this point in perspective in a very human-friendly manner. The code is available in the description below. Now that I know the absolute orientation of each camera, I can input those into the master node, which is the laptop. The network architecture looks something like this. 3 camera nodes are connected to a laptop via 2.5 GHz Wi-Fi radio, and the laptop queries each camera at 5 Hz or every 200 milliseconds for voxel data. Once it receives this voxel data, it then fuses them together and then passes it on to the server at 2 Hz or every 500 milliseconds. As the laptop gives the server new data, it is placed into a sliding 10-frame temporal window. Then, at a 3 Hz refresh rate, the server passes this 10-frame temporal window into a U-Net-style Minkowski engine convoluted neural network as a 4-dimensional spatio-temporal object. This allows the neural network to infer where the target's position is based on previous frames of the voxel data, not just the most recent one. This allows for extremely precise positional data even when the input voxel data is scattered. Oh, sorry, that was extremely boring and I fell asleep. Let's get to the actually interesting part. It's time to look at the resulting data. This animation shows 3 types of data: voxel, heat map, and real target position. The voxel data is displayed as multicolored cubes and usually looks like lines going from the cameras to the target. The heat map data, also known as the positional prediction data the neural network outputs, is displayed as a red blob. The real target position is displayed as a green sphere. Together, these datasets tell a very clear story. What you're looking at here starts as raw camera footage, a low-cost 720p sensor, no zoom, no special optics. In each frame, the object of interest occupies only a few pixels, often at the edge of visibility, sometimes barely distinguishable from background noise. This animation displays what happens when that data flows through Aries. Each point you see represents a detection candidate extracted from the image. Most of them are irrelevant. Noise, compression artifacts, sensor quirks. Aries evaluates all of it, frame by frame, and isolates a handful of pixels that actually matter. As the animation progresses, those isolated detections begin to form a trajectory. This is the critical moment. The system is no longer reacting to individual frames, it's reasoning over time. Even when the object briefly disappears or blends into the background, the track persists. That persistence is not hard-coded, it's learned by the convoluted neural network. This test was designed to answer a very specific question: does the neural network trained on synthetic data behave the same when exposed to real sensors? And the answer is yes. The same failure modes, the same noise patterns, and the same uncertainty that were modeled in simulation appear here in the footage. And more importantly, the network responds to them in the same way. The features it learned were not artifacts of a clean training environment. They transfer over. That's why this testing campaign's result matters so much. It shows that Aries can operate at the limits of visibility using inexpensive hardware without relying on ideal conditions. The data you're looking at isn't filtered or cherry-picked. It's a system working from end to end exactly as deployed in real time. From here on out, everything builds on this foundation. The accuracy of Aries becomes even more apparent when you switch to a top-down view. In this perspective, each frame is no longer just an image, it's a spatial estimate. The ground plane is fixed, the camera is known, and every detection is projected into world space. The red marker you're seeing represents Aries' predicted target position. As the animation plays, notice how the marker moves. It follows the same path as the target and responds smoothly to changes in motion. There is a small expected delay as new observations are incorporated, but the estimate remains tightly coupled to the target's true position. What's important here is what you don't see. You don't see the predictions oscillating as raw detections fluctuate. You don't see it snapping between false candidates. Instead, the model continuously reconciles uncertainty and converges on a single, stable solution over time. This top-down view makes something very clear. Aries isn't reacting to noise or guessing frame by frame, it's maintaining a coherent track of where the object is moment by moment. Finally, let's switch to a close-up view where we can directly assess how the prediction compares to the target's true position. At this scale, the offset between the two becomes measurable. Based on the computed results for this run, the positional error remains under 0.8 meters. That error includes sensor noise, projection uncertainty, and the inherent delay introduced by filtering. For context, a typical GPS receiver on a consumer drone is accurate to roughly 1.5 to 3 meters under good conditions. What you're seeing here is a vision-based tracking system that operates within tighter error bounds than a typical GPS, using just 3 cameras and no external positioning system. This comparison is important. It puts the results into real-world terms and highlights the level of spatial precision Aries is achieving using passive sensing alone. And there you have it. That's all I have for the moment. Aries is a continually developing program, and I expect to have more results here in the near future. So definitely stay tuned. Aries can evolve into something that can not only track drones, but can also track stealth aircraft as they fly over the United States, or let's say Taiwan, countries like that, countries of interest who might need protection from stealth aircraft here in the near future. So I will be modifying Aries to fit that particular use case. That's all I have. Adios.